So we'll now start a new chapter, LP spaces. The LP spaces or the Lebesgue spaces are Banach spaces which are a very rich source of examples and counterexamples in functional analysis, and they also very naturally occur in many applications of mathematics, especially the study of partial differential equations. And so these spaces are very important, and they have such interesting properties. So first we will look at some basic properties. Okay, so X S mu measure space and F X to R measurable function. We are dealing with real valued functions, but many things, almost everything that I say will carry over to complex valued functions also. Okay, so 1 less than or equal to P less than infinity. Define norm Fp equals integral over x mod f to the p d mu whole power 1 by p. So we say f is p integrable if norm Fp is finite. So integrable if p equals 1. So when p equals 1, this is just a notion of integrability, and square integrable if p equals 2. Otherwise we call it p integral. Then let m be positive, and we set mod f bigger than m. This is the short notation for the following set of all x in x such that mod fx is bigger than m. Similarly, you can say mod f less than m, less than or equal to m, greater than or equal to m, etc. We have the corresponding notation. Okay, now define norm f infinity as the infimum of all m such that mu of mod f bigger than m equal to 0. Okay, so this means the function is bigger than m, f of x is bigger than m only on a set of measures 0. So then you call this m and as a kind of is almost an upper bound. It's because almost everywhere fx is less than or equal to m, and so the smallest such number, the infimum of all this, is called the essential supremum. So this is called essential supremum of f. Okay, and we say that f is essentially bounded if norm f infinity is finite. Okay, so we have now defined some kind of so-called norms within inverted commas. We will see that it's not precisely the case. Okay, so then definition: 1 less than p less than infinity, the conjugate exponent of p is p dash defined by 1 by p plus 1 by p dash equal to 1. So if p equals 1, conjugate exponent is infinity, p dash equals infinity, and vice versa. Lemma: 1 less than p less than infinity, p dash conjugate exponent, then ab greater than or equal to 0, then a power 1 by p, b power 1 by p dash is less than or equal to a by p plus b by p dash. This is actually the generalization of the AMGM inequality, because if you write p equals p dash equal to 2, then you get square root of AB, which is the geometric mean, and here you get a plus b equal by 2, which is the arithmetic mean. So this is the generalization of the AMGM inequality. Okay, so let us prove this general inequality, which is very useful in many ways. So let t be greater or equal to 1. Consider the function f of t equals k times t minus 1 minus t power k plus 1. And where k belongs to 0, 1. So k is between 1. So what is f dash t? F dash t is equal to k into 1 minus t power k minus 1. And this is greater or equal to 0 since k is less than 1 and t is greater or equal to 1. Okay, and therefore, and since f of 0 equal to 0, f of 1, and f is increasing in 1 infinity, and consequently you have that t power k is less than or equal. So this function has to be always non-negative. F of t, so implies ft is greater than or equal to 0. So t power k is less than or equal to k times t minus 1 plus 1. Now if a or b equal to 0, result trivial. So you can assume a is positive, b is positive. So without loss of generality, you can assume that a is greater or equal to b, strictly positive, because p and p dash are conjugate exponents of each other. So the result is symmetric in p and p dash. So it doesn't matter which one you are going to take, and so you take t equal to a by b and k equals 1 by p. So this will be less than 1 and this will be greater or equal to 1, and then apply star. So star is this inequality, and you will get diagonal. Okay, so this is a proof of a very useful inequality here. So now proposition. So this is called Helder's inequality. Let 1 less than or equal to p less than infinity and p dash conjugate exponent. If f is p integrable and g is p dash integrable, essentially bounded if p equals 1, then integral over x mod fg d mu is less than or equal to norm fp norm g P dash. So proof. So let us take P equals 1, P dash equals infinity. Then mod fx gx is less than or equal to mod fx into norm g infinity almost everywhere, because for almost every x, gx is less than or equal to norm g infinity. That's what we have seen, and this is true. So now if you integrate, so integral over x mod f g d mu is less than or equal to integral mod f d mu over x into norm g infinity, and that is exactly double star. Okay, so because this is equal to norm f1. So now we assume that 1 is less than p less than infinity. So this implies, of course, that 1 is less than p dash is less than infinity as well. And then again, double star trivially true if norm f p or norm gp equal to 0, because in that case f or g equal to 0 almost everywhere. So we can assume that norm f p not equal to 0, norm g q p dash not equal to 0. So assume norm f p equals norm g p dash equal to 1. Then apply lemma to mod fx power p mod gx power p dash. Okay, then what will you get? You have to take mod fx gx is then less than or equal to mod fx power p by p plus mod gx power p dash by p dash. So if you now integrate, then integral mod fg d mu over x is less than or equal to integral f of x power p is 1, because norm fp assumed is equal to 1, so you get 1 by p. Similarly there you get 1 by p dash, but by definition that's equal to 1. For general case, apply this to f by norm fp and g by norm gp dash, then you will get double star. So remark, when p equals p dash equal to 2, Helder's inequality is the same as the Cauchy-Schwarz inequality. That is integral mod fg d mu over x is less than integral mod f square d mu over x power half integral mod g square d mu over x power half. So then we have the next proposition. This is called Minkowski's inequality. One less than equal to p less than equal to infinity, fg p integrable essentially bounded if p equals infinity. Okay, then f plus g is also p integrable, and norm f plus g P is less than or equal to norm Fp plus norm Gp. So this shows that P integrable functions form a vector space, and you have the triangle inequality for this norm, for this thing which we have called a norm. It's not yet a norm, we will see in a moment. Okay, so proof. So mod fx plus mod gx plus gx, is less than or equal to mod fx plus mod gx. So this implies, let us call this triple star for p equals 1 or p equals infinity, because that's obvious from this inequality. So we can assume that 1 less than p less than infinity. Again, result trivial if norm f plus gp equal to 0. So okay, that's, I am jumping the gun a bit, so let me not say that. So now f g p integrable and t going to t power p is a convex function. So by definition of a convex function, you get that mod fx plus gx power p by 2 power p should come is less than or equal to 2 power p minus 1 of mod fx power p plus mod gx power p. So this implies that f plus g is also p integrable. Just integrate both sides, you will get this. So triple star trivial if norm f plus gp is 0. So without loss of generality, assume norm f plus gp is not equal to 0. So we are now going to write mod f of x plus gx power p d mu x. This is less than or equal to integral over x using the triangle inequality fx plus gx power p minus 1 mod fx d mu x plus integral over x mod fx plus gx p minus 1 gx d mu x. So we want to apply Helder's inequality to each of these terms. So we will, for f is in p integrable, therefore I can apply here. So I want to know if the first term is p dash integrable. So let us take mod fx plus gx power p minus 1, so into p dash. So we want to know if this function is integrable. But what is, this is p minus 1, p dash is nothing but p dash minus p dash, but p plus p dash equals p dash, okay, and therefore p dash minus p dash is nothing but p, and therefore this is equal to mod fx plus gx power p, and that is integrable. And so what is norm fx f plus g power, norm of mod f plus g power p minus 1, what is its norm? It's p dash norm. So the p dash norm is nothing but power 1 by p dash into the integral over x of the function here, so f plus g power p d mu, because that is what this p dash power, and that is equal to nothing but norm of f plus g p over p by p dash, because this thing is nothing but the pth power of the norm, and therefore you have that this is f plus g power p by p dash. Okay, so now having done all this work, so now we apply this to Helder inequality to each of the terms here by Helder. So what is the left hand side? Left hand side is f plus g whole power p. So norm f plus g p whole power p is less than or equal to, now we want the p dash norm of this function, so norm f plus g p by p dash into norm fp, and similarly the other term would give you norm gp. This will give you norm fp and this would have given you norm gp. Okay. Now you can, because f plus g p is not 0, so you can divide, and then p minus p by p dash is nothing but 1. Because 1 by p plus 1 by p dash equal to 1, so 1 plus p by p dash equal to p, so p minus p by p dash is nothing but 1, so you get norm f plus g p is less than or equal to norm fp plus norm gp. So this proves the Minkowski's inequality. So now if you look at, so p integrable functions form a vector space, and if you take norm fp, this of course greater or equal to 0, norm of 0 p is 0, norm of f plus g p is less than or equal to norm fp plus norm gp, and of course norm of alpha f p, this is trivial to check, is mod alpha times norm fp. So it shows everything which is similar to a norm, but norm fp equal to 0 only implies that f equal to 0 almost everywhere. It is not f equal to 0. So this is the problem. So you cannot make it a norm. So what we are going to do is to do the usual thing we do in mathematics, namely quotient out the difficulty. So we say f is equivalent to g if f equals g almost everywhere. Okay. Now if you take the equivalence classes, form a vector space. Why? So if you take f is a represent, so if you take two equivalence classes, say f and g, you take a representative this thing, because if f1 is equivalent to f2, g1 is equivalent to g2, then f1 plus g1 is equivalent to f2 plus g2. Okay, and alpha f1, and then alpha times f equals alpha f. f1 is equivalent to alpha f2, and therefore any representative you take through pointwise addition and then take the equivalence class, then you will get the so this forms a vector space, and norm p is constant on each equivalence class, because if f and g, that is f equivalent to g, then norm fp is the same as norm g p. So you don't have to worry, you can define the norm as the norm, so norm f p equals norm fp. This is well defined, and now it is a norm, because if norm fp equal to 0, This implies that f equal to 0 almost everywhere, that is f is equivalent to 0, that is the equivalence class of f is the same as the equivalence class of 0. So using these equivalence classes, we will define a normed linear space. So definition: X S mu measure space 1 less than or equal to p less than infinity. The space of all equivalence classes under the equivalence relation of equality almost everywhere of all p integrable functions is a normed linear space with the norm of an equivalence class being the p norm of any representative of that class. This space is denoted LP of mu. Okay. The equivalence classes of all essentially bounded functions is a normed linear space with the norm of an equivalence class being defined as the infinity norm of any representative. This space is denoted L infinity mu. So we are talking of equivalence classes, but actually we will be working with a representative of every equivalence class. So whenever we will say LP function, but what we are really talking of is not a function but a equivalence class of functions, but all the functions in the same equivalence class are equal to each other almost everywhere. So any computation you do, especially integration related computations, it doesn't matter which representative you take, because if two functions are equal almost everywhere, then the integrals are all preserved, and therefore we will remember that we are talking of equivalence classes, but we will not make a fuss. We will just say function in LP. It means we mean a function which is equivalence class of a p integrable function or essentially bounded function. So this is the notion. Okay, so now that we have defined the LP spaces, next time we will take up some of its properties.